Have you ever been on a train in a station, looked out the window, and seen another train that looked like it was moving, but you weren't able to figure out if it was your train or the other train that was moving? That's relativity. The first step to understanding relativity is knowing how to use a space-time diagram. First, we have a one-dimensional space, aka a line, which represents a train. You can move left or right along this line. Now let's introduce a second dimension, but instead of another spatial dimension, it will be time. And if we make the same movement in our 1D train, our path will move forward along time as well. Moving with constant speed results in a straight line. This is called a world line. In the case of our two trains, the origin represents one end of each train. This time axis is the time for the train you are on, and the world line is the time axis for the other train. Since you are on the train, it appears stationary, and thus doesn't move along the x-axis, but the other train will move, keeping its origin on the world line. However, if we shift our perspective to the other train, our train now appears to move backwards, and that train is stationary. Yet the final result is the same, so there is no way to know which train moved. This is the basis of relativity. In order to further understand relativity, let's use the simplest clock, a beam of light bouncing between two mirrors. As with the trains, if you are stationary or moving with the clock, you observe the clocks to act the same. The distance between the mirrors can be written as the speed of light c times the time it took as observed by an observer with a relative velocity of 0. However, a stationary observer would observe the light in the moving clock to trace a longer path, thus taking more time. But just how much longer? This can be calculated with the assistance of Pythagoras' theorem. Using Pythagoras' theorem, and with a few steps of simplification, we will eventually arrive at the simplified formula, where the time measured by a stationary observer is equal to the time measured by a moving observer times a constant gamma. This constant shows up frequently in relativity and is called the Lorentz factor. At low speeds, it is approximately equal to 1. But as you approach the speed of light, it grows to infinity. Using these formulas for relativistic time and space, and with some manipulation, we can arrive at the formula for relativistic speed. These formulae are used to describe a Lorentz transformation. An object moving with constant speed on a space-time diagram will trace a world line. With some simple math, we can see that this angle is equal to the speed of the object divided by the speed of light. Using the formula for relativistic time, when t prime equals 0, we can rearrange and find that the x prime axis should make the same angle with the space axis as the world line makes with the time axis. Drawing lines parallel to the space and time axes of both the stationary and moving observer, these diagrams can be used to calculate the space and time coordinates as seen by both the stationary and moving observers.